right? I thought there'd be data. Is anyone out there?
Okay, welcome back to Mathematical Statistics. We have just finished a brief intro to confidence intervals, and we will come back to confidence intervals once we know how to estimate things. And I wanted to do a similar brief intro to hypothesis testing. And I know you're anxious to figure out how to estimate things, and so am I. But historically, I've discovered that doing this intro now really makes it easier to understand when we hit full-on hypothesis testing later, because hypothesis testing is really notationally heavy, and you'll have some time for some of this stuff to sink in before we really need it. So I went back and forth about this a lot last night, but I think we should do this as well. And then after this, we start method of moments estimators, and then the MLEs, maximum likelihood estimators, and then the MVU. Okay, so today is called a brief intro to hypothesis testing. And it's a lot of notation and language. And so again, you'll have a chance to absorb that by the time we do like real heavy duty hypothesis testing. And if you've done any hypothesis testing before, like obviously, well, not obviously, but I bet it was data oriented, and this is not so data oriented. And so some of this is going to be a little boring, but some of this I think is worth your time. There'll be a few things in here that will look a little more general. So let's start with an example. Suppose we have x1, x2, etc. through xn, IID, normal, mu, sigma squared. One of the biggest things we're going to do here is take away normality, because almost every test in a data-oriented course depends on things being at least approximately normally distributed by the central limit theorem. But we're going to get to go pretty crazy and do tests based on all sorts of different distributional assumptions. So in this example, I'm going to assume that sigma squared is known. Just like with confidence intervals, it's a building block. We'll get rid of that. And so we want to look at the sample, and there's some true mean mu sitting out there, like for the overall population. And from the sample, we want to determine whether, in this example, mu is less than or equal to 3, or mu is greater than 3. So the way you're going to do this is you're going to look at the sample counterpart to the mean mu. So you'll probably look at the estimator of mu, that is x bar. And just because x bar is above 3, that doesn't mean that the mean is above 3, right? Especially if it's close, because you know the true average Calc 2 score on exam 3 could be 3, I guess. But if you get a sample of 10 people, you might easily see it above 3, and that doesn't mean the true mean wasn't 3 or less. So this is going to depend on the distribution of this guy and how much error we're willing to accept in making this decision, because we can't know for sure which of these two things is true based on our sample, because we may have gotten one like freaky sample. Okay, so yeah, so not only are we going to take away normality, but we're going to take away, in this class, we're going to be able to test much more general things. We're going to leave behind inequalities, and we're going to be able to test whether or not a parameter theta is in some strange region versus not in the region. So it won't have to be just a simple less than something or greater than something. Okay, so some of you already know, I'm sure, the definition of a null hypothesis. This is something that we're going to denote by like an HO and H0 really. And so this is something that is always assumed to be true. You never really prove that a null hypothesis is true. you assume it's true, and you look at the data and you see if you have strong evidence to not believe it's true. So assume to be true unless the data strongly suggests otherwise. Okay, so an example of how we might write down a null hypothesis would be to just to say H0 is the hypothesis that mu is really less than or equal to 3. And so if we go into our data, our x1 through xn, we're going to assume that mu is less than or equal to 3, unless the x bar, our sample mean, is so much larger than 3 that we really can't go with the idea that mu is less than or equal to 3 anymore. And so we have an alternative hypothesis. So we're going to denote this. Some people use it like an HA for alternative. I'm going to use the other common notation, which is an H1. Seems more mathy than using A for alternative. I don't know. If you want to use an HA, that's fine. But it is what you are out to show, what you are out to prove. Okay, so as an example, the alternate hypothesis for our silly starting example would be that mu is greater than 3. And technically, the two hypotheses together should make up the entire parameter space, but they might not for reasons that we'll get to. So maybe we'll have a null hypothesis that says that the mean is 3 versus the mean is greater than 3. And let's say it's still the normal distribution. So we're leaving out a lot of mu's. But the assumption behind that test, or at least behind the mathematics, is that those are the only possible values for the parameter. There is no concluding that mu is actually less than 3. So if you're testing something a little simpler, you are just thinking about the parameter space as being shrunk. Okay. Stop me if you have any questions, but I was saying at the beginning here that, you know, in Stat 101, whatever that means, we're usually restricted or limited to, in these hypotheses, seeing things like less than or equal to, greater than or equal to, less than, equals, not equals, things like this in our hypotheses. But here we're going to get really general. So in MathStat, we're going to have a model, right? We're going to have some x1 through xn. They're going to be IID from a PDF. I think I already talked about my semicolon notation. Tell me if I haven't. But I want to stress the dependence on a parameter theta. And I think I talked about if you use a line, then it looks like you're being Bayesian, which is, if you want to do that, that's fine. But we're going to test things like, actually, before I can write the test, let's suppose that, so this is one version of a capital theta, kind of a theta with some lines on the top and bottom. I'm going to let this be the parameter space. So if we're talking about the mean mu of a normal distribution, this will be everything from minus infinity to infinity. And if we're talking about lambda for an exponential distribution, this will be everything greater than 0. So we want to test, or we will test, so not in this simple introduction part, but when we get to actual hypothesis testing, we're going to test the null hypothesis that the parameter is in some subset of the parameter space that I'm going to call like capital theta naught. So that's just going to be some subset versus the alternate hypothesis that theta is in the rest of the space. So I'm going to use this notation, the capital theta. This is a set minus notation. So it's everything that's in here and not in here. I mean, it's literally means that you take this set and you intersect the complement of this set. Does that make sense? I didn't mean, I mean that entire thing. Sorry. So it's everything that's in the parameter space, but outside of the things being considered in the null hypothesis. And this can get pretty wild. It's not always describable by a simple inequality. Could be like, test the hypothesis, take x1 through xn IID exponential with rate lambda, and test the hypothesis that the sine of lambda is greater than 0.5. I don't know why you'd want to do that, but you can. Okay, so not only are we going to do more general things, we're definitely going to be dumping normality. All right, so eventually. But in our basic intro to hypothesis testing, first thing I want to do is define for you what is meant by the words a simple hypothesis. So a simple hypothesis is one that, if it is known, it completely determines the distribution for you. And I'll tell you exactly what I mean by that with examples. But this is one that completely determines the distribution. There's a common mistake made in like intro stats. I mean, it's not a mistake probably on the instructor. They just don't want to get into this conversation. But there's a common mistake in beginner stats to think that this is a hypothesis with an equal sign in it. And that's not necessarily true. So let me finish writing this definition. Completely determines the distribution. And then before I do examples, the alternative, otherwise, it's said to be a composite hypothesis. Okay, so this should be cleared up by my examples, hopefully. Okay, so suppose we have a random sample from, let me make some bullets here, 3 examples. So we have x1 through xn IID normal, mu, sigma squared, and sigma squared is known. Which I keep saying it is kind of silly that you would not know mu and know sigma squared, but it is a building block. So the null hypothesis that mu equals 3 is simple. Because if you know that it's true, then you know exactly what distribution x1 through xn came from. The normal distribution with mean 3 and variance sigma squared, which is known. So in the same setup, the null hypothesis mu is less than or equal to 3 is composite, because if you know that it's true, you still don't know exactly what distribution you're dealing with. It could be the normal 2.5 sigma squared, it could be the normal -10 sigma squared. There's a whole lot of distributions. There's a whole lot of normal distributions with means below 3. And the thing that is sometimes kind of overlooked is that in this other setup, so I'm going to suppose that x1 through xn are IID normal mu sigma squared, and then both of these parameters are unknown. In this case, the hypothesis that mu equals 3 is actually composite. So it looks simple because it's equal to a number, but the point is that if you know it's true, you still don't know exactly what normal distribution you're talking about, because there's a whole bunch of different ones in there depending on what sigma squared is. So there's a tendency in beginner data courses to say equal sign is simple and anything else is composite, but here's an example of having an equal sign in there and it's still composite. So the next thing we need to talk about are the idea of errors in hypothesis testing. There is a reality out there, and that reality is that the null hypothesis is true or that the null hypothesis is not true. And then you make a decision. You reject that it's true. You don't think it's true because you look at the data, or you fail to reject that it's true. So it's kind of like an innocent until proven guilty thing. There is no proving there's no proving of innocence. There's proving that you're not guilty, I guess. So you don't ever say you accept the null hypothesis when you look at data. And let me make a little table and completely ignore what I'm going to completely ignore what I just said, because I would like this table to be kind of nice and easily readable and binary. So on the left side, I'm going to have reality, and that is that the null hypothesis is true or it's false. And then I'm going to have two columns representing our decision after we look at the data. So the only possible decisions are going to be that you reject the null hypothesis or you fail to reject it. But just this one time, I'm going to put except in quotes just to make it a nice, like, binary looking table without all the double negatives. So your null hypothesis might be that mu is less than or equal to 3, and maybe you have a normal distribution, and maybe the sigma squared is nice and small, like 1. And if you look at your x bar and you see something really large, like 18,209, then this is kind of strong evidence, although we'll make that formal, that this null hypothesis is not true, and that we should go with the alternative, that mu is actually greater than 3. But it's entirely possible that the true mean could be less than or equal to 3, and you see this value of x bar, and that's because the normal distribution goes on infinitely, right? So if you have a mean of 3 and a standard deviation of 1, which brings you to those points of change of concavity, it is really, really unlikely that you're going to see, oh, actually, and then you take a sample of size n, and that will give you a distribution for x bar, which is going to be even thinner, right? Because we get variance sigma squared over n. Then seeing x bar being 18,209 is really, 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 really unlikely. But technically, it's possible. And so that's the mistake you can make in hypothesis testing. It's not your fault. It's just that, you know, if you saw that giant x bar, you would probably reject this null hypothesis and go with this alternative. And there's a slim, slim chance that you could be wrong about that. So filling in the table, if the null hypothesis is true and you fail to reject it or quote unquote accept it, you did good. If it's false and you rejected it, you did good. Otherwise, you've made one of two types of errors. And so in the upper right box here, this is known as a type 1 error. That means the null hypothesis is true, but you rejected it. And the other one is a type 2 error. So with these types of errors here, I now can define for you the idea of a, I'm sure you've heard of, no, I'm not sure. So it's entirely possible you got here without taking any statistics. That would have been me when I was in your position. And I actually moved from a math PhD program to a stats PhD program, never having had stats 101, never having heard of a variance or anything like that. So I'm not sure where you guys are, but here's a definition of the level of significance of a test. And this definition is going to change depending on, that's not exactly true. I could give you a universal definition, but I'd rather do it in a building block kind of way. So I want to give you the definition just for a simple null hypothesis first. And then when I give you the universal definition that will work for simple and composite null hypotheses, you'll see that it corresponds to this definition. So this is just a special case. Okay, so for a simple null hypothesis, the probability of making a type 1 error is called the level of significance of the test. It's also called the size of the test for reasons that we will see in this course, because it's kind of measuring the size of a set. So the probability of making a type 1 error is the level of significance or size of the test. Okay, level of significance or size. I say size a lot more than I say level of significance, because maybe because I can't say that. I say size a lot more than I say level of significance because it makes me feel more mathy because we're measuring. It connects to measure theory and measuring sizes of sets. But you can say whatever you want, and it is denoted by an alpha. And so this has to be set by the interested parties before you do the test. As the statistician, it's not your job to select an alpha. It's you are constructing a hypothesis test for someone out there in the world, and it's up to them to figure out how much error they're willing to have for both of these types of errors. And I guess before I go on, let me say that yeah, I might as well do this. So for a simple alternate hypothesis, oops, these definitions get a little different when the hypotheses, wow, what is my problem today? These get a little different when the hypotheses are composite. And again, the definitions will mesh. But for a simple alternate or alternative hypothesis, we use a beta to denote the probability of a type 2 error. And then as a quick definition, 1 minus beta is known as the power of the test. Okay, so a bunch of words here. Alpha and beta, they have an inverse relationship, but they do not have a 1 minus relationship necessarily. There are plenty of examples when they do. Sorry if you're trying, I'm going to come back to this, but I'm going to scroll back up to my table. So in here, the probability of this type 1 error is alpha, and the probability of the type 2 error is beta, and they live in completely different universes. So it's not like one of the event is the complement of the other, because you either have the null hypothesis is true or it's false. And so if you're in the case when it's true, if the type 1 error happens with probability alpha, then that means you did the right thing with probability 1 minus alpha. This and this should add up to 1, those probabilities. This and this should add up to 1, but not these. However, there is definitely an inverse relationship, because if you want to minimize making a type 1 error, then you're going to make it really, really hard to reject your null hypothesis. And so it's likely you're going to reject, you're going to make it really hard to reject the null hypothesis. So it's likely you're going to fail to reject even when you should. Let's get to some examples. There's definitely like an inverse relationship, but it's not a 1 minus because they live in different universes. The null hypothesis, I said, is something that's always assumed to be true, and the alternate hypothesis is something you are out to show. Not necessarily out to show. You might not want it to be true, but let me try to give an example. So suppose it usually depends on what side of an issue you fall on. So if you run a potato chip company and you make 16-ounce bags of chips, you probably, you don't want to, I don't know, you don't want to make your customers mad. You want to make sure you have at least 16 ounces in your bags of potato chips. So you'll grab a sample and you'll compute the X bar, and you'll maybe try to test the null hypothesis that mu is less than or equal to 16 ounces, and the alternative that mu is greater than 16 ounces. This is the potato chip manufacturer trying to say, I'm sure we've put at least enough in there. But if you're the consumer advocate group and you're yelling with your torches in the street because the chip company is ripping you off, then you're going to assume that the true mean is greater than or equal to 16, and you are out to prove, like to make your case, that really the true mean is less than 16. So this again is the point of view of the manufacturer, and this is like the point of view of the public in this particular example. And there's definitely a symmetry here, but you, in either case, say that in this case, you can accept this or fail to reject it. And yeah, accepting this doesn't really mean you've rejected this, to answer your question specifically. Accepting the null hypothesis here means that you tried to find evidence of the alternate, but you couldn't find it in your sample. So there's definitely, I mean, you can write a test either way, right? And your test, maybe you're on this side and I'm on this side. When you reject the null hypothesis, I will probably I definitely will accept the null hypothesis. So it can go either way. You don't actively accept or reject the alternate hypothesis, though. You just believe the null hypothesis is true, and then you say, wow, the data strongly suggests this is true, so I'm going to go with that. Or the data was not strong enough to suggest that this is true, but I still don't really know, but I'm at least going to say, I think this is true. People usually care about alpha more than beta. You can set alpha ahead of time, so whoever the potato chip company is going to set alpha for you, or the doctor trying to, that's having you check out his newly designed pulse oximeter is going to tell you ahead of time what value of alpha and or beta he or she is willing to accept. So if you set alpha, your beta is, this conversation isn't going to work until we do an example. You can set one, the other will be automatically locked in, or you can free up more parameters, which will allow you to set both and kind of achieve a balance. Let's just do an example, the stat 100 example. Okay, so I'm going to go back to the normal distribution and looking at a mean of 3 or greater than 3. And then to simplify this, also because we only have a level of significance defined for a simple null hypothesis, I'm going to simplify my null hypothesis. So suppose I have x1 through xn, IID, normal mu sigma squared. And sigma squared is known. If you really want it to look known, you could just, I think you guys can handle it. So usually I would say, let's just fix it as a number, but I'm going to put sigma squared where sigma squared is known. Okay, so suppose that we want to test the null hypothesis that the mean is equal to 3 versus the alternate hypothesis that the mean is greater than 3. So you'll see that I have not used the entire parameter space because really the mean can be anywhere from -infinity to infinity. So I'm kind of simplifying the problem here as a building block. So there is no concluding that the mean is less than 3. What we could conclude here depends on our sample size and our sigma squared. But if you observe an X bar of -3 million, you're going with the mean is 3. You're not saying the mean is less than 3. That's just not a possibility. It means that you didn't have evidence to say that the mean is greater than 3. Okay, so suppose that we observe, we have our sample of size n, and we observe an X bar. I'm going to have an actual value, so I'll make this look lowercase, of 3.2. The question is that large enough above, is that high enough above 3 to go with the alternate hypothesis? And that is quite large if you had a very large n, right? Because the variance for X bar is sigma squared over n. And if, it's possible that the true mean is 3, but you made this distribution so skinny that you can't get to 3.2 with any reasonable probability. So totally dependent on the n and the sigma squared. So I don't know what to do with this. We should look at it while it's still random, because that's what math stat people do. So I'm going to find sorry, I don't want to write hypothesis test. The hypothesis is already here. So I'm going to find a test of size or level of significant alpha based on the sample mean. Just like with our confidence intervals and various estimators, at this point, I'm still giving you the thing to base it on, and that's changing as soon as we finish hypothesis testing. So it might be based on a minimum or maximum or sample variance or something, so I'm going to give you that statistic. If you view an X bar, the only way you're going to believe that the true mean is greater than 3 is if, first of all, if X bar probably needs to be greater than 3, and it needs to be significantly greater than 3, whatever that means. So maybe seeing a 3.2 is not going to be enough to say that the true mean is greater than 3. So we get what is known as a rejection rule. And so this is also something that I call the form of the test. And it's going to be to reject the null hypothesis in favor of the alternative, which is kind of important to say here because there's other possibilities in this parameter space. So in favor of H1, if X bar is greater than some number, which I'm going to call C, where C is determined to give a size alpha test. There tends to be a feeling that the form of this rejection rule has to match the alternate hypothesis, but it really doesn't. Suppose maybe you don't want to write this because it'll mess up your example, but I do want to say something kind of on the side here. Suppose that we had an exponential distribution with rate lambda, and we had a random sample x1 through xn from this exponential distribution. And suppose we're testing whether or not lambda is 3 versus the alternate hypothesis that lambda is greater than 3. And suppose we're making a test based on X bar. So your rejection rule or region, you want to look at this X bar and you want to look for evidence that the alternate hypothesis is true. And for this distribution, the larger the lambda is, the smaller the values coming out of the distribution are. There's two ways to see that. One is that the PDF starts at lambda and goes down, right? So if you have a larger lambda, then because the total area has to be 1, it's going to shoot down like super fast. And that's going to give you, this yellow curve is going to give you more values closer to 0 than the white curve is going to give you. But another way to see this is, we know that the expected value of x, which is the expected value of x bar, sorry, I can't really fit that, is 1 over lambda. So larger lambdas mean smaller values coming out of the distribution. And so the rejection rule is going to be to reject the null hypothesis in favor of the alternative if X bar is actually small. Small meaning below some C, for some C to be determined. So your rejection rule really comes from looking at your statistic and looking at when the alternate is true and then trying to relate those, but it's not always a simple, oh, this is greater than, so my rejection rule is going to be greater than. All right, so I'm going to leave this exponential example and go back to the normal. I did say that we would reject the null hypothesis in favor of the alternative if X bar is greater than some C where C is to be determined. So let's determine it. Let's find that C. And this is going to depend on a given alpha, which is the size or level of significance of the test. So let's find C. And just to be clear, I'm back to the normal example. Okay, so we're going to use alpha for this, and alpha is the level of significance that's been given, which is usually like a 0.05 or 0.01 or 0.1. Those are the 3 most common alphas. But this is the probability of a type 1 error. And if you go back to my table, This is the probability that the null hypothesis is true, but we reject it. So we reject the null hypothesis when it's true. And rejection for us, because we figured out the kind of direction the test would have to go, rejection for us is going to be observing X bar greater than C when the null hypothesis is true means that mu equals 3. Okay, so I started with a normal distribution. So X bar is going to be normal. And if we're restricted to this case when the mean is 3, then that tells us the mean. And the variance is whatever was given over the sample size, which is known. I have a normal distribution, so I know X bar is still normal. If the mean is 3, I know the mean for X bar. I know the variance for X bar because both sigma squared and n are assumed to be given. And so how do you compute any probability like this? You standardize it. You take X bar minus its mean over its standard deviation, and you could do the same thing to the right side. And usually you do it symbolically on the left side and numerically on the right side. So I'm going to take away the mean of 3 over sigma over the square root of n when mu equals 3. And it's important to write at this point when mu equals 3, because if mu is 4, then this is a normal, but it's not a standard normal. But if mu is 3, then I can call the thing on the left a z. And then I'm going to write after this line where z is standard normal. And now I've kind of used up the information that mu equals 3, so I'm going to stop writing it. So just one more time, this guy is not a standard normal if mu is not 3. We're kind of under the assumption that the null hypothesis is true. Okay, so we know how to find this. We have a symbol for it. So just to recap this here, this is what I'm working with, and we're trying to find the C. And so we can find a number that Z is above with probability alpha. If you draw a picture, you have your standard normal PDF. And you're looking for a number that you are above with probability alpha. And this is a critical value that we've already named little lowercase z sub alpha. So this question mark has to be this critical value, lowercase z sub alpha. And then going back up to the line right above, that means that the c minus 3 over sigma over the square root of n has to be this critical value, which comes from a table if someone gives you the actual alpha. And then you can solve for c, and you get little z sub alpha sigma over the square root of n plus 3. And then as a final step, and I think I can keep these straight in a step 1, step 2, step 3, and step 4. So I'll do that in my next example. You finally pull it all together and give a conclusion. And you say, my test is that I will reject the null hypothesis in favor of the alternative if X bar is greater than Z sub alpha sigma over the square root of n plus 3. But I really tried to keep that, not plug and chug formula in a box, because we're going to want to generalize this to different distributions. So we don't want to just follow a list of rules. We want to follow kind of the general idea, which would be step 1, come up with a statistic on which you'll base your test. Step 2, come up with the form of the test, like how will that statistic reflect that the alternate hypothesis seems true. Step 3 would be to come up with critical values for the appropriate distribution. And then step 4 will be to have a conclusion. So we'll do a lot more examples, but questions on this? I will get to type 2 errors next time, but let me say now why I define the two types of the level of significance and size of the test for just a simple null hypothesis. Because what if we instead had like a new example where I have x1 through xn, a random sample or IID from the normal distribution with mean mu and variance sigma squared, and sigma squared is known. And suppose I want to test the null hypothesis that mu is, someone say something? Just heard some strange feedback, which sounded like myself. Okay, that mu is less than or equal to 3 versus the alternative that mu is greater than 3. You would go through the exact same steps. So step 1, you'd come up with a statistic. I'm really rushing here. And you would take probably an estimator of mu. In class, I will tell you what the statistic is. Step 2 is the form of the test. So you're assuming that the true mu is less than or equal to 3, but you're going to reject the null hypothesis in favor of the alternative if x bar is large, i.e. x bar is greater than c for some c to be determined. Okay, so step 3 would be to find c. And so you would say alpha is the probability of a type 1 error. And I'm out of time. Let me just finish this line. This is the probability we reject the null hypothesis when it's true. And this is the probability that x bar is greater than c when the null hypothesis being true means that mu is less than or equal to 3. And the problem here is that I can't standardize this and compute it if I don't know the actual value of mu. I have a whole range of values, which is why we're kind of stuck here unless we define alpha differently. So I'm out of time, but we will define the probability of a type 1 error, the level of significance, as the maximum probability of making that mistake. And we're going to maximize it over everything in the null hypothesis. So we're going to finish that up next time. We're going to look at the power of the test, and we'll do one like exponential example, and then we'll go on to estimating. But historically, I found that this really helps when we do hypothesis testing later because you have a chance for the language to sink in a little bit. So thank you.